So, you locate OC by constructing a triangle OA, OB, OC, which is similar to AMB, but that is with the actual locations of OA and OB. Okay. To determine the link lengths, it is easier to do it using Cayley's construction, where essentially you first you have your coupler triangle, okay, which is AMB, okay, and then then you have, you take the length of OBB and make it in line with AB to do the Cayley construction, and similarly OAA also you do that. Then you construct a line from OA that is parallel to AM. Okay. Construct a line from OB parallel to BM. Okay. This you mark as OC, but that is not the actual location of OC. You should. Now, you just extend M and this parallel. From M, you just extend this and you extend this. Okay. And then through M, you draw a line parallel to the base. Okay. So, this will be A1, this will be C1, okay. This will be B2, this will be C2, and the link lengths therefore will be, so the coupler base you can get the link lengths off of this construction for the two cognates. And then when you construct it, you would actually construct it as, okay, if this is the location, actual location of OC, then you know your C1 may be here, and this will be say the actual location of OA. So, A1, C1, and this would be M. So, your actual link would be something like this, the cognate. Okay. In space, it would be located such that it is at the actual locations with link lengths obtained from the Cayley construction. Okay. So, because there were some questions after class about this, I thought I will repeat that. Now, this, so if M is away from the coupler base, right. So, that AMB forms a triangle, this is valid. Suppose M lies on AB, okay, either between A and B or beyond A and B. This is still valid, the cognates still exist, okay. The construction is slightly different, you have to do it because doing this essentially means this triangle is essentially collapsing, okay, because M lie on AB, then everything else also. So, how do you determine the link lengths for that case? So, we will do an example. So, here is a given 4 bar OA, AB, OB, and you are given a coupler point M which traces this coupler curve. Okay. You want to find the cognates that correspond to this 4 bar, that will generate the same coupler curve. Okay. So, this is the procedure. Okay. So, from you have OA, you have OB, the original linkage, and This is your given linkage, this is the point M. I shouldn't put a, I should just put a, because we use the open circle for the pivot, this is just the coupler point M. Okay. Now, you want to construct the coordinates for this. So, look at this here. If you look at the original, let me copy that over. Yeah. So, you will construct OAA1, okay, parallel to AM. Yeah? Oh, no, I can't. Okay, good. Okay. And from M, M A1 is parallel to OAA. Okay. So, from here this will help you locate the point A1. Okay. On the other side, from OB parallel to OB, you have parallel to BM. Okay. So, you have this. So, B1 will lie here and then from M parallel to OB. So, this intersection will give me B2. Okay. Now, I need to find this OC, C1, C2. I do not have a triangle anymore to construct OC, but I know that OC will divide OA, OB in the same ratio as M divides AB, okay, when you collapse. Okay. So, I use the fact that OC divides OA, OB in the same ratio as M divides AB. Okay. So, if I take this distance, then I locate OC here such that OA, OC by AM equal to OC, OB by BM. Okay. I still need to find C1, okay, C1 and C2, which you can see here. C1 is parallel to, no, let us see, we created, so C1 divides A1M, again the same thing. If you collapse this triangle, okay, just as, because M is now collapsed onto AB, C1 will divide A1M in the same ratio as M divides AB. Do you see this? These two triangles A1 C1M is similar to AMB. Okay. Therefore, C1 will lie on AM such that the ratio A1 C1 by C1M is again the same as AM by MB. AM by MB, same ratio you will locate C1. This is collapsing onto this, just as M collapses onto AB. Similarly, here C2 will collapse onto MB2. So, if I have MB2, I have C2 here, such that M C2 by C2B2 equals AM by MB. I will do that in blue. Okay. OCC1 should be in black. This is that, and OCC2 should be in blue. So, now my two coordinates are OA, I think I have them separately here. So, this is the construction and the two coordinates are OA A1 C1, and now M actually lies outside of AC, okay, when we divided that, and then the other coordinate is OC C2 B2 OB. Okay, you have what I had as the black one here. Okay, I should. This is one coordinate, this is this coordinate, and this is this coordinate, and this is the coupler point here. So, you can see here that this linkage is a lot more compact than the original linkage that we started off with. You can see, because OB, OC are really close together here. So, this is what we meant by saying that it can give you something with a more suitable sizing for the space that you have. So, this may be more suitable, it really depends on the application, but you can explore alternatives by using the Roberts-Chebyshev theorem. Okay. And so, in your original coupler, the point was actually between A and B, but in your two coordinates it can be located outside of the coupler base that you get, that does not matter. Similarly, you can find coordinates, if I give you this linkage, it will give you these two as your coordinates. So, I can construct the coordinates using whatever I want as my original linkage. I will get the same, I will get the same three, the set of the same three linkages, okay, no matter which one I start from. So, if you look at you have omega 3 and say omega 4. I am just assuming they are all, it could be the directions could be different, but so my original 4 bar I have these velocity relations. I can relate those because of the fact that they are connected by parallelograms. So, if 2 has velocity omega 2, then A1m, which is a part of 9, will also so omega 2 will be the same as omega 9. Okay. Now, C1m is part of link 9 and it is parallel to link 7. So, omega 7 will also be equal. So, those 3 angular velocities will be equal. Similarly, omega 3 is parallel to omega 10. So, link 3 has any line on link 3 will have the same angular velocity, right. On the rigid body all the lines will. So, omega 3 will be the same as omega 10, okay. And here omega 3 will be the same as omega 5 in this cognate, because MB is parallel to OBB1. And then omega 4 is going to be, because MB1 is parallel, omega 6 will be equal to omega 4 and therefore, omega 8. So, in the given left cognate, right cognate, this is omega 2, this is omega 9 equal to omega 7, omega 3 in the given linkage is equal to omega 10 in the left cognate and omega 5 in the right cognate, and then omega 4 in the given linkage is equal to omega 8 in the left cognate and omega 6 in the right cognate. So, it is a cognate is essentially just a linkage of different geometry which generates the same coupler curve. Okay. So, if you look at, if the original linkage is a Grashof crank rocker, okay. So, let us say original linkage is a Grashof crank rocker, just say, then one cognate will also be a crank rocker, okay. Okay, let us just say original cognate 1 will also be a Grashof crank rocker, the other one will be a Grashof double rocker. So, it will also have one link that makes a complete rotation, but it will be the coupler link. When I say Grashof double rocker, it is called, or I should just use the previous notation where GRCR. So, this is okay, crank rocker rocker, crank rocker, sorry, rocker, the coupler is the crank, makes the full rotation rocker. So, this will be cognate 1, cognate 2.
Can you predict whether the left one or the right one is
Once you do the construction, yes.
Without finding the link lengths.
Without finding the link lengths, you only know that these are you, and also how what you designate as, it will depend on these velocity relationships, right. You without determining the link length, once you determine the link lengths, then you can do it. See, the cognates have different link lengths from the original linkage. So, you have to determine the cognates before you can say which, and it also will depend on which one you give as your input, right, because it depends on the inversion. What you give as your input, right. So, you have to determine the link lengths of the cognates, but you know that in general you will get. So, if you have the original one is a crank rocker, you know you will get another cognate which is a crank rocker. Okay. To have the same, so let us see.
Can't you say that, say second one is a crank, link 2 is a crank.
Link 2 is the crank, okay.
Then because of the velocity relationships, we know that link 9
Right,
also
right.
has a similar velocity. And
So, link 9 has a similar velocity. So, if I give an uniform angular velocity to link 2,
doesn't that automatically imply that 9 is a double rocker?
yes, in that sense, yes. So, this will mean that 9, if you to get the coupler point to trace the coupler curve at the same speed, you would have to give the input to 9. The same omega 2, if you give omega 2 here, then in that cognate you would have to give omega 9 to get, if you want to traverse the coupler point at the same speed, because these two are equal, right. That is the relationship you have to maintain. Okay. Or in the case of the second cognate, you would give the input to omega 7, omega 2, omega 9, omega 7. So, that would be your crank rocker. Okay. This, in this case, this is not a crank rocker. The diagram that is shown here, the linkage, it may not satisfy the Grashof conditions for a crank rocker.
Assuming that it does satisfy, doesn't the left cognate automatically become the double rocker?
It depends.
Assuming that second is a crank for the given linkage.
Yeah, you could say that. Yeah, because of this velocity relation. If the original linkage is a double crank, okay, where the fixed link is the shortest link, Grashof double crank where the fixed link is the shortest link, then the cognates will also be double cranks. Okay. So, if this is G C, I will just write it as double crank or drag link, because all three links will make a full rotation. The two cognates will also be double cranks. And if it is a triple rocker, then the cognates will also be triple rockers. Triple rocker meaning non-Grashof. In this case, this is the shortest link. OAA is the shortest link. Therefore, if this is a Grashof mechanism, that will satisfy the condition. Shortest link can make the full revolution. The link adjacent to the shortest link is fixed. In this case, even though this is, if you look at A1 C1, it need not be the shortest link. So, I do not know whether you can predict right away that this will be the.
But madam, omega 8 and omega 10 are not making completive relations.
Omega 10 and
Omega 8.
no, see this is not the right figure to be looking at if you are going to do it for a crank rocker. I would suggest that you do it for a crank rocker and then look at what you get. Trying to make conclusions about a crank rocker from this figure is not going to help, okay, because so whatever will be the shortest link, that will be the, and if it is next to the fixed link, then you will get a crank rocker. That is what I meant by saying that it depends on the inversion, right.
But we should be able to prove it because all of them are related by a scaling.
Try it. Yeah, try it. I am not saying it is not possible. I am saying you do it. It should be possible. Take a crank rocker, take something that satisfies Grashoff's criterion and then derive the cognates for that. Okay. The other common application for coupler curves is their use as approximate straight line linkages. So, there are various versions of these straight line linkages. So, you will have approximate straight line portions. You will not get an exact straight line, but you could have approximate straight line portions in the coupler curve that you could use as a straight line linkage for the application. So, for instance, this is the Evans or grasshopper, I think I have. You can see the approximate straight line portion. Here it is just being actuated between these two limits, but it would actually trace the full coupler curve. They are just not showing that in the animation. Okay. So, this is the Evans, or this is actually a cognate of that, sorry, this is the Watts linkage, sorry, which is a cognate of the Evans linkage. You can see the coupler curve is, so this, if you imagine that this is flipped over, okay. So, you have the straight portion, a figure 8, these are from two different sources, so they do not look, but the Watts linkage and the Evans linkage can be derived as cognates of one another. Okay. They trace the figure 8 coupler curve, which has a fairly straight portion. Then you have the Roberts linkage, where the point P traces between the two fixed pivots, it traces an approximate straight line, point M, sorry, M here, P here. Okay. So, that is your Roberts linkage, and then you have the Chebyshev linkage. Again, they are only showing it, but this could actually potentially make a full rotation. You have, it traces this coupler curve which has a straight line portion. Okay. And the Hawkins linkage is a cognate of the Chebyshev. The Hawkins linkage can be derived as a cognate of the Chebyshev, and you can see here the coupler point is like the problem that we did, where the coupler point is between the points A and B on the coupler base. The Hawkins linkage, the coupler point moves outside that coupler base when you derive the cognate for that, for this linkage. And that, so these have different names because they were independently derived. Later on it was found that one is a cognate, one can be derived as a cognate of the other. Okay. So, they were, straight line motion was something that, coupler curves was something that people wanted to use for approximating straight line motion. So, different people came up with these different linkages, and then it was found that some of them are cognates of one another, but that is why they have different names. They are named after whoever invented them. Okay. If you want an exact straight line, so approximate straight lines can be generated by 4 bars using appropriate coupler curves, but if you want exact straight lines, you typically have to go to more number of links. And one of the famous linkages that traces an exact straight line is called the Poisselier linkage. Okay. So, and it has 8 bars actually. So, this is just to tell you that, yeah. So, this you can see that it traces an exact straight line that is perpendicular to the line joining the fixed pivots.